and eigenvector. They're all complex. So let me see. I will spend 10 minutes to talk about the MATLAB command and remind you some pitfall. You need to be cautious. Start from an easy one. If you want to find the eigenvector A, you just type the A. This is a 3 by 3 matrix. And you specify the format. This means rational numbers. Will give you fractions. And the commander is EIG. It's the 3 letters of the eigenvectors or eigenvalue. And put A. On the left hand, you have 2 matrices. They're both 3 by 3. The V is made by 3 columns, and each column represents the eigenvector. And the second matrix D give you the 3 eigenvalue, lambda 1 equal 1, lambda 2 equal 1, repeating lambda 3 equal 10 on the major diagonal. That's how MATLAB write down the eigenvalues. So if you go to the detail of the definition, let me call the first one for lambda 1. This is V1. Second, V2. This V3. You should realize this A times V1 equal, let me put it this way. A times V1 equals lambda 1 V1. And A times V2 equal lambda 2 V2. A times V3 equal lambda 3 V3 by definition. If you put this A on the left, V1, V2, V3 on the right hand, then you can put these 3 equations together into one equation. And on the other hand, you can say V1, V2, V3 times this D, which is lambda 1, lambda 2, lambda 3. So the D is really, let me write out the D, 1, 0, 0, 0, 1, 0, 0, 0, 10. I will let you go home to check the detail. This first row will equal this, the same. The second row will equal this times this. And the third, column, I'm sorry, column. The third column, A times this, equals this V times the 10. It's the same expression, but just put the 3 together. So the summary is to check if you got it right or wrong. All you need is to check the A, V. Now this V is not a vector, it's a matrix, equals VD. 3 by 3 times 3 by 3 is a 3 by 3. And the left, both sides are 3 by 3 matrix. And if you look at this, individually, each is a 3 by 1. Can you see it? They just put all 3 together. Well, you need to take time to get used to this. Now, this is how we check by MATLAB. When you finish it, don't forget just one line to check. Look at the AV on the left, look at the VD on the right hand. What you find? No? They're the same. Let me just scroll down. They're the same. It's really a little bit ugly than you think you like. Do by hand, at least you can say 2, 2, 1. For this one, a parallel 2, 2, 1 instead of divided by 3. but that's all right. Well, MATLAB really did the most of the time numerical calculation, unless you want to use a symbolic. But the symbolic package of MATLAB really is the Maple. They're just merged. Well, let's look at what danger this round arrow could give to us. Please go home to check the notes. This is the defective matrix I gave in the example 5, the last example for the previous lesson. If I make this C equal the defective matrix we have, we remember this matrix only got one triple root, which equal 1 as the diagonal matrix. As a defect matrix, by the way, I'm sorry, defect matrix. And only have 2 eigenvectors. But let's see what this MATLAB tells us. If you use the same command, try to find the eigenvalue and the eigenvector, they give you all similar structure, a 2 3x3 matrix. The weird thing, you look at these eigenvalues, what you find? See, 109774, the denominator is 109775. All you see is very close to 1, right? And the second one, 219551, 219950, and the same here. They really is a result of a round arrow. That's the arrow. It really means it equal 1, but because the computation made some error, and then it become close to 1. If that give you the round arrow, they also give you those nonsense eigenvectors. It really does not exist, because we know it's defective from the previous example. The only answer really is the eigenvalues, right, this one. And then you say, whoa, that's wrong. You may try to check the error, let the C times the V2, and see if they equal V2 times D2, they might give you the same answer, because they come from the same round arrow. But the Maple also warn you with those symbols, means you check by hand. Could be wrong. Could be have some rounding error. Means rounding up, rounding down, those things. Because it's a numerical package. Another defective matrix is more interesting. This time I used the format long. Last time we used the rational, remember? And this is a defector 4x4 matrix. And when you look at the answer of the eigenvector, the eigenvalue is right. They have a repeating triple root equal 2, and the single root equal 3. And actually, this defect eigenvector, if you compute it by hands, it's going to be, it have 3 independent eigenvectors. The 3 one is this 1 0 0 0 0 that associated with our number 2 equal 2, and this one is the repeating eigenvector. Now it's independent, related with the repeating eigenvalue 2, and that's the third one related to the number 1 equal 3, the single one. And this is our result from manual computation. But you look what the MATLAB give to you. This actually is right, 1 0 0 0 0. The second is right. This is all associated with the 2 and the 2. The third one does not make any sense, because give you a bunch of zeros, And this one actually is right, but not as pretty as we like here. -4, -3, 4, 0, 1. Let's compare. -3, 4, 0, 1. If you multiply this by 4 times, and this really is 4 times of this, and the first one is really -3 times of the last one. So these two are parallel, the same direction. The last one is also right. So you get one wrong there. It's a defective matrix. Well, you might figure out now why I call it defective. If you do computation, they give you some junks. You need to be careful, understand it, then you can avoid it. So the last one I give you is the complex matrix. There's no difference. You just need to realize this I is imaginary. I do not know if this is on the denominator or on the numerator. But anyway, the only thing I want to tell you is compared to the handwork, that's much better looking. And you can make your choice to choose your free variable. Because a human being can make an intelligent choice, then your answer will look so nice. But the MATLAB really got a bad choice. That's why it looks so ugly. But it's fine, as long as you get it right. You can still finish the work, especially when it's too big. You cannot do by hands. The lesson I wanted to bring to you is you have to understand your result, especially as an engineer. And the computer won't take responsibility for any of those mistakes.